The normal distribution is the most important continuous probability distribution. This is because many random processes in nature and economics are approximately normally distributed. It is really a family of continuous, unimodal, and bell-shaped curve. Let's explore it in greater details. The probability density function f of x for normal distribution is represented by this algebraic formula, where x can be any value between positive and negative infinity. Mu represents the mean. Sigma is equal to standard deviation. E is equal to 2.71828, or what is known as the natural constant. And pi is equal to 3.14159, or what is known as the geometric constant, commonly known as the ratio of circumference to diameter of a circle. You do not need to memorize this formula, but you do need to know that for this family of normal curve, the shape of any particular member will depend on the two descriptors, the mean mu and the standard deviation sigma. This whole idea can be symbolized as the random variable x has a normal distribution n with mean mu and with variance sigma squared. This is how the normal distribution looks like. Some characteristics of the normal distribution are that 1. It is bell-shaped and symmetrical. So the left side of the curve and the right side of the curve are mirror image of each other. 2. The mean is equal to the median, which is equal to the mode, and they take the central position on the horizontal axis. 3. The two tail ends are asymptotic, so they approach and get very close to the x-axis, but never touching it. And 4. Since this is a probability distribution, the total area under the curve is equal to 1. Since the curve is symmetrical, the left side has an area of 0.5 and the right side also have an area of 0.5. The shape and position of the normal distribution depends on mu and sigma. Let's look at curve 1 and curve 2. Both are normal distribution with the same shape and size. However, curve 2 is to the right of curve 1 because mu sub 2 is greater than mu sub 1. If we add in this curve 3, we notice that it is spread out more than curve 1. This is because although mu sub 1 is equal to mu sub 3, such that the centralized location is the same, the variability sigma sub 3 is greater than sigma sub 1. So the spread of curve 3 is much wider than curve 1. Regardless of the shape and size of the normal distribution, there are some known properties that applies to any normal curve. The first diagram shows that approximately 68% of the area under the curve is within one standard deviation from the mean mu. The second diagram shows that approximately 95% of the area under the curve is within two standard deviations from the mean. And the third diagram shows that approximately 99% of the area under the curve is within 3 standard deviations from the mean. And awareness of these known properties will help to decipher a lot of info about a certain distribution, as can be seen in the next example. The GPA of students in a school ranges from 0 to 4, is normally distributed, and has a mean mu of 2.7 and has a standard deviation sigma of 0.4. So in the normal distribution curve, The central location is the mean of 2.7. Using the known properties of normal distribution, we know that about 68% of the area under the curve is within one standard deviation from the mean mu. About 95% of the area under the curve is within 2 standard deviations from the mean. And about 99% of the area under the curve is within 3 standard deviations from the mean mu. In the first diagram, mu plus sigma is equal to 3.1 and mu minus sigma is equal to 2.3. So we can infer that 68% of students obtained a GPA of between 2.3 and 3.1. In the second diagram, mu plus 2 sigma is equal to 3.5. Mu minus 2 sigma is equal to 1.9. So we can infer that 95% of students obtained a GPA of between 1.9 to 3.5. In the third diagram, mu plus 3 sigma is equal to 3.9 and mu minus 3 sigma is equal to 1.5. So we can infer that 99% of students obtain a GPA of between 1.5 and 3.9. All these info will give us a good indication of the actual spread of the GPAs. In this example, we have 2 schools with drastically different GPA system. For school A, the GPA range from 0 to 4 is normally distributed with a mean of 2.7 and a standard deviation of 0.4. For school B, the GPA ranges from 0 to 9 and is normally distributed with a mean of 6.1 and a standard deviation of 0.8. A university wants to admit only the top 0.5% of each school. How should they pick the students? Here's the normal curve for school A with a mean of 2.7. And here's the normal curve for school B with a mean of 6.1. Using the known properties of normal curve, we know that 99% of students obtain GPA that is within 3 standard deviations from the mean. So for school A, 99% of students have GPA that lies between 1.5 and 3.9. For school B, 99% of students have GPA that lies between 3.7 and 8.5. Now, 99% of the area under the curve has been shaded. That leaves us with 1%. If we divide equally between the tail ends, each tail end will get 0.5%. And this top 0.5% is what the university is looking for. So for school A, only those with GPA that is greater than 3.9 will be admitted. And for school B, only those with GPA that is greater than 8.5 will be admitted.